Let's take a look at reflection, refraction, and diffraction. But before we think about those phenomena, let's think about a different way to depict waves. So far we've really thought mostly about waves kind of from an edge-on or a side view situation. So like if we're imagining waves on the surface of the water, let's say I have a source right here, and we've thought about the ripples moving away from the source like so. But now think about what that would look like from above. Well, if we have a source right there, and we're looking at this from above, you might think that you would see ripples moving outward. And the ripples here might correspond to the high points of the wave, the crests of the wave surface. Well, these are examples of wave fronts. Wave fronts are a line where all the points are moving in phase. Now, I think it's often easiest to consider wave fronts at the location of the crests, but you don't have to. These wave fronts that I've drawn could just as easily be the location of all the troughs, or any other part of the wave that's moving in phase. Now, another thing that we're going to have is the ray. A ray is an arrow which shows the direction of the wavefront motion and the direction of the energy transfer. So for this situation, here's the rays. The rays show us that the wavefronts are moving in those directions, outward away from the source. Now, something that is always true. The ray and the wavefront are always perpendicular to each other, no matter the situation. So for example, if I had wavefronts that looked like this, where they're parallel, the ray may look like this, perpendicular to the wavefront at every location. Notice also that the shortest distance between adjacent wavefronts is a wavelength. Okay, so on to the phenomena. So imagine that we have a wave, and the wave is approaching the boundary between two mediums, or media. Well, I'm going to draw the rays for that situation. So here's medium 1, here's medium 2. I'm going to have an incoming wave, and again, this is the ray for that wave. When the ray hits the boundary, or sometimes they say is incident upon the boundary, the ray can do one of two things, or the wave can do one of two things. It can either continue into the new medium, or it can reflect off the boundary. If it reflects off the boundary, it might look like this. If it passes into the new boundary, it might look like this. The reflecting off of the boundary is, of course, called reflection. Passing into a new boundary, or excuse me, into a new medium, is called transmission. We call the phenomenon, however, where it passes into a new medium and is changed, refraction. So that's altering the wave when it enters into a new medium. And one thing that remains constant, so many things might change in this reflection and this refraction, but one thing that always remains constant with the wave is the frequency. So that's going to be key. The frequency always remains constant, even when the wave passes into a new medium or reflects off the boundary. Now, for reflection, we have a rule called the rule of reflection. The rule of reflection is that the angle of incidence is equal to the angle of reflection. Now, what do I mean by those two angles? Well, let me draw the diagram. Here's our incoming ray. Here's our reflected ray. The angle that I'm talking about in this rule is this one. It's the angle between a normal line, a line normal to the boundary, and the rays. So here's the angle of incidence. Here's the angle of reflection. All right, so that's not too bad. Now, the law of refraction is a little more complicated. So first of all, it's often called Snell's law instead of the law of refraction. And before I write down the law, I'm going to draw the situation. So here's our boundary. We have medium 1, medium 2. Here's our incoming ray, and here's our ray that passed into the new medium, the ray that was transmitted into the new medium, the refracted ray. So to get a relationship between all of these things, we need a couple of defined quantities. So, for example, we're going to need something called an index of refraction, which is represented with a lowercase n. The index of refraction is something that's particular to each medium. It's a way to measure how much that medium interferes with the wave speed of the wave. So, for example, a high value of n means that that medium slows down the wave a lot. A low value of n means that, relatively, it does not slow down the wave very much. Okay. We're also going to need to define a couple angles. The angles that we talk about in Snell's law are always going to be defined from a line that's normal to the boundary. So I'm going to draw a line that's normal to the boundary, and I'm going to write in the angles that we're going to think about. Okay. The relationship between all of these is given by Snell's law. So I'm going to write that down. N1 over N2 is equal to the sine of theta 2 over the sine of theta 1, which is also equal to V2 over V1. All right, that's a lot. So N1 and N2, those are the indices of refraction of each of the medium. So N1, that's the index of refraction for medium 1. N2, index of refraction for medium 2. Sine of theta 2. Okay, well, theta 2 is the angle that we're talking about in medium 2. So it's this angle right here. Theta 1, that's the angle that we're talking about in medium 1. So right here. And V2 and V1, well, V2 is the wave speed in medium 2, and V1 is the wave speed in medium 1. And that's how they're all related. That's called Snell's law, or the law of refraction. Now, if we go back to this index of refraction for just a moment, we can write down an equation for the index of refraction for an electromagnetic wave. For an electromagnetic wave, the index of refraction is equal to c over v, where c is the speed of light, and v is the wave speed of the electromagnetic wave in the medium. So you can see, for vacuum, n would equal just 1 over 1, or actually 3 times 10 to the 8 meters per second over 3 times 10 to the 8 meters per second. So for a vacuum, n equals 1. Turns out, for glass, the index of refraction is approximately 1.6. For water, the index of refraction is approximately 1.3, and for many plastics, the index of refraction is approximately 1.5. So that gives you an idea of what indices of refraction tend to be for electromagnetic waves. So let's think about some of the trends that we would see in refraction. So let's draw a diagram, and let's have a low index of refraction material and a high index of refraction material right here. And we're going to have an incoming ray like that. If we have a situation like this, the angle of incidence will be greater than the angle of refraction. Okay. If you go from a high index of refraction to a low index of refraction, we'll get something like this. The angle of incidence will be less than the angle of refraction. Now, you could prove this with a little bit of trigonometry, but we're not going to go through that. Just trust me. But I want to point out a situation that's a little bit odd. We can have an arrangement if the wave goes from a high index of refraction to a low index of refraction. We can get a situation where the angle of refraction is equal to 90 degrees. And it would look like this. Now, that's a little bit odd, because is that really transmission? Because the refracted ray didn't really go into the new medium. It's just traveling along the boundary. And if the angle of incidence was any greater than this, then no wave would enter the new medium. The entire wave would be reflected into the old medium, into the original incident medium. In that situation, we would call that total internal reflection. Now, going back to that situation where the angle of refraction is 90 degrees, in that situation, we call the angle of incidence the critical angle. That is the greatest possible incident angle we can have before we get to total internal reflection. Now, if this all seems a little bit weird and a little bit pointless, it's very, very useful in certain situations. So, for example, an optical fiber, this is how they get light to travel through optical fibers without losing any light. In an optical fiber, there's always total internal reflection inside the optical fiber, and so no light is lost. Okay. I also want to draw another situation. I want to draw the situation where we have a wave going from low N to high N. Okay. I'm going to draw the rays. So that's old news. But now I'm going to draw in the wavefronts. So watch what happens. If I do that, remember, the guiding principle here when we're drawing the wavefronts is that they have to be perpendicular to the ray and they have to be equally spaced. in that medium. Now, when they enter the new medium, look what happens. They're closer together. So what does that tell us about the wavelength? Well, when we went from a low N to a high N, the wavelength decreased. The wavefronts are closer together, so the wavelength is smaller in the new medium. Now, if I went from a high index of refraction to a low index of refraction, this is what the rays would look like. And now let's draw in some wavefronts. Remember, wavefronts are always perpendicular to the ray, and in a single medium, they're always equally spaced. So if I do that, if I follow the rules, you'll see in the new index of refraction, in the new medium, the wavelength has now increased. Now, the last phenomenon that we're going to look at is diffraction. And diffraction is the situation where we have waves passing near an obstacle. And it turns out if that happens, when they pass by that obstacle, the waves can change direction. A little bit strange. So, for example, if I have two obstacles like this with a little window in between, and I have wave fronts coming toward that little window like this, and here are the rays, when they pass through that little window, when they pass near these obstacles, turns out that the wave fronts on the other side will look like this, and the rays will look like this. The waves that have passed by the obstacle are said to be diffracted. And it turns out that the waves right here that are kind of moving straight through that opening or aperture, they will tend to have a higher amplitude. And the ones that have been diffracted more, these on the side, they will have weaker amplitudes. Now, there's no change in the wavelength when we talk about diffraction, just change in direction and amplitude. And the biggest effect is when the aperture or the opening is roughly the size of a wavelength. If the aperture is much larger than a wavelength, we won't see much diffraction. If the aperture is much smaller than a wavelength, we also won't see much diffraction. But then again, if it's such a small aperture, we wouldn't get much wave passing through it anyway.